We are getting ready to graduate. Well, maybe not college yet, but we're getting ready to graduate into the multi-step synthesis of organic chemistry. Yes, that's right. These synthesis problems are now going to get tremendously more complicated. Can you believe that? Who would have ever seen something like this coming in a chemistry class? Well, chain elongation is going to be a tool that we will use because all of the other examples that we've seen before, we started off with 4 carbons, we ended up with 4 carbons. We started with 6 carbons, we ended up with 6 carbons. We started with 8 carbons, we ended up with 8 carbons. How can I start off with 3 and get 6? At no point in time have we talked about that yet, but we can do it. The alkene reactions are not going to allow this to happen. So this is a special alkyne reaction reserved just for them to make them feel a little special. It makes you love and hate the alkynes at the same time. So chain elongation basically means this is a way that we can increase the number of carbons in a chain. And the only way that this can happen as of right now is using the acetylide ion. That's the only way. How? How do we do it? Well, let's use our words. Let's use the terms that we have been discussing this whole semester so far. And let's start putting these pieces together in a beautiful manuscript. If I take an alkyne, and it's got to be a terminal alkyne, at least on one side. Now, it can be terminal on both, a hydrogen on the left and a hydrogen on the right. That's perfectly okay. Or some kind of random alkyl group out here. Doesn't really matter what it is, as long as a hydrogen is present. I could take one of these two, and I could add sodium amide to this reaction. In the previous video, we talked about amide, didn't we? This was an NH2 minus group. Where does that come from? We don't order that in a bottle. It's got to come from somewhere. We can't just order a negative ion like this and expect people are going to ship it to us. It's got to be all or nothing. So typically, just like what we've seen before with like hydroxides, we don't just order OH in a bottle. That OH has to come from somewhere. It's typically sodium hydroxide or potassium hydroxide that dissolves and it frees up the OH. Well, sodium amide really suits that same type of purpose. So sometimes they will write NaNH2. Other times they will just write NH2 with a negative, and that is it. That's all that they will do. Nothing more than that. Either which way they do this, it means the same thing. So this is going to be the first step of chain elongation. Take an alkyne, react it with sodium amide. I have an acid and a base. The acid will lose the proton, and this will create my triple bond with the minus, or if I'm using that other choice, one of these carbons might have another kind of carbon group on it, which is perfectly okay, not a big deal, but it rips one of the acidic protons off of there, fulfilling the definition of an acid. And I'll end up with NH3 at this point, but I'm not even going to write that down because it's going to confuse you. So we're just going to pretend like that doesn't even exist. That's the first step of chain elongation. Take an alkyne, react it with amide, and get you a negative. Get you that negative. You need that negative piece. Why? Because we need to elongate it. And what is that called? Folks, I don't know about you, but that negative charge, this is a great nucleophile. This thing is great to fulfill a nucleophile role in a reaction. So if I could take that piece, whatever that piece is, maybe it's a terminal one still like this one, or it could be this R group that carbon's carrying around with it. That's not a problem, just a little extra baggage. It's okay. And if we could react this with an electrophile, we can make these two pieces come together in a magic little marriage, like Snow White, Sleeping Beauty, finding their princes. There you go. But we need an electrophile. Okay, so what do we use? Well, we're talking about chain elongation, so it looks to me like I would probably want to pick something that carries some carbons with it. We can. So I'm just going to randomly write down like CH3, CH2, CH2. And I need something in here that really disturbs that carbon bond. I want something unequal. I want something that maybe is electronegative. I want something that can easily be removed. I want something that's maybe a little bit bigger so it can take care of itself. And folks, the best choice here are brominated compounds. Why? Bromine has electronegativity. Bromine wants electrons. Bromine is very large. If you look at the halogen group, it's one of the largest that we always talk about. It's bigger than chlorine. It's bigger than fluorine. And the bigger it is, the more adult-like it is. And if it does carry a negative charge, well, the size alone can help neutralize that out. So it doesn't really disturb bromine. And now we put it in motion. So, this alkyl bromide, this R group can be anything it wants to be. I just randomly chose 3 carbons. There's a tug of war. Bromine says, I'm big, I'm bad, I want these electrons. And bromine sucks them up. If that's the case, then this bromine will be slightly negative, and this carbon can't put up a fight, so this is going to be slightly positive. And then over here on the acetylide side, we've got these negative pieces that are out there searching for someone or something to satisfy its need. Now, rules of mechanisms. Start at your negative source. Oh, it's going to be one of these. I'll start it here. We'll do that top one. Point it to the positive source. Okay, that's a review. I'll point it to the positive, so that's this carbon here. And that carbon says, bromine, I've had enough of you. You have griped and you have moaned and we have fought this entire time. If you want those electrons, by golly, take them. I'm done. It's over. Never call me again. Take me out of your cell phone. Delete me as the contact. And delete me from Snapchat and Facebook and everything else. And bromine says, okay, I thought you would never say so. See ya. And it takes those electrons and it goes. So what do we form? Folks, we've got this piece here. This hydrogen with that carbon. That triple bond, which is still there, by the way. I mean, we didn't do anything to that triple bond. This negative acetylide ion, that carbon made an attachment to that partial positive carbon. So there's the CH2 for that one, and then the CH2 from that molecule, and then we ended it with a CH3. We have just elongated the chain. And then we've added this bromine as like a side product that just kind of floats away because we don't really care about that. We don't do anything else with it at this point. This is how we elongate a chain at this point in the class. It's with an acetylide ion and an alkyl bromide. So I have taken a 2-carbon system, right here. And I have turned it into a 1, 2, 3, 4, 5 carbon system. We've elongated a chain. We've done it on the rules of acid-base with step number 1. And then we did it on the rules of nucleophile and electrophiles on step number 2. And really, kind of honestly, they're the same. Well, the other choice would have worked the same way, just whatever else was here on this particular carbon for that R group, well, that is just what would have been attached here as well. There is no difference here. However, this choice might be a very good option. And here's why. If I had a carbon triple bonded to a carbon, and that's it, acetylene, that's all, and I add amide to this, this is going to give me the acetylide ion because it came from acetylene. That's great. We can elongate it from that point. We can do whatever we want to do. All right, so at this point, I can add in a random carbon group with a bromine on it. And what I'll end up with is this hydrogen carbon triple bond to a carbon with that random alkyl group. Whatever was right here, that's what's going to get glued and stuck onto that carbon, and poor little bromine that poof goes away. But folks, we don't have to be finished at that point yet, because look, we've got another hydrogen on the left-hand side that can be ripped off again. The only thing that we have to do at this point is take this and add amide to it one more time. And now we can rip that other hydrogen off. So we'll get a carbon that's triple bonded to a carbon that had that new R group added on from the first step. And then we can go in and add on another group. It could be the same. It could be different. I don't really care. The problems will tell you what it is. And then a reaction will happen again. And we will get this new R group, I'm representing that with 2 dashes, onto a carbon that's triple bonded to a carbon that had that very first R group that was added from the first step. We can elongate a chain on both sides of these, which is going to make these even worse. But I told you, we're upgrading. We're going to be flying first class before this is over. And this is how we elongate a chain. Okay. In addition to this, I also want you to keep this in mind. After the elongation, we still have a triple bond. So all of those reactions that we've just discussed from the alkyne and alkene family, they still hold true. And that's where these problems are going to get weird. Because now what I'm telling you is that in the beginning, we can take an alkyne, amide it to get acetylide. And then we can elongate that chain to make that molecule bigger. We end up with still an alkyne. And then we can add HBr. We could add water acid. We could add Br2Cl2s. We could add mercuries. We could add borohydrides. We could add platinum. We could add platinum or hydrogen and Lindlar. We could do any of those reactions from the alkyne and alkene world on top of those synthesis steps that you're seeing right now. Oh gosh, you're getting nervous. Oh gosh, you're starting to sweat. I know. So let's do an example. It says, you've got one butene. And you need to make that molecule. Folks, you're good like this now. Bet you didn't see it coming, did you? You are good. You're learning organic. You're becoming synthesizers. I'm just giving it to you in little drips and drips throughout the lecture series. The problem is that we need to learn how to put all of this together. That's the issue. Maybe looking at it individually in each individual sections in a nice little box aren't too bad. Oh, I add water, acid, I can do that. Oh, I add Br2, I can do that. Oh, I can add H2 and platinum, I can do that. But now, taking all of those boxes, we need to dump them all into the same room. Lids open, scatter it all up. And we need to be able to make sense of all of these individualized concepts and put it into one problem. That's what something like this is like. So let's test our organic synthesis ability. And here we go. Here's our first example. Let's look at this. 1, 2, 3, 4. 4 carbons in total. 1 butane. Over on the right-hand side, we have 1, 2, 3, 4, 5, and 6. We have 6 carbons. 6 carbons here, 4 carbons there. I need to elongate, don't I? Okay, well, I only know one way to elongate at this point. That's it. One way. How do I do it? Well, I'll take the alkyne that they give me in the problem, and I'm going to amide it. I'm going to put NH2 on it. There we go. Well, when I do that, what I create is an acetylide ion. I take that hydrogen and I rip it off. That's the purpose of adding the base, because this is going to act as an acid. So what I end up with is a CH3, CH2, carbon, triple bond carbon that carries a negative charge. Now, I'm not going to write the byproducts. That has nothing to do with me anymore. I'm focused solely on the organic pieces, and that is it. So that did make NH3, and poof, away it goes. Okay, so I've not elongated anything yet. The only thing that I've done is rip the hydrogen off. I need to elongate. How many more carbons do I need? I need 2 more carbons, right? I need to go from 4 to 6. 1, 2, 3, 4, 5, 6. So I need to add 2 more carbons in here. So here are the 2 carbons that I need to add right there. Well, what else do I need to bring in it? I need the alkyl bromides. That's how this works. So there's the RBr group. And now I have a nucleophile and an electrophile. So this CH2CH3 piece, that is going to go onto this negative acetylide ion at this point. So I'm going to rewrite this as now CH3, CH2, carbon, triple bond, carbon, and then CH2 and CH3. This CH2CH3 that I've added on came from this piece that was on the bromine. I've spliced the 2 things together. That's what I've done. But I'm not yet finished, am I? Because if I look at my product, what do I have? A C double bond O. Well, that is not a C double bond O. But it doesn't matter. You should know that from your Batman tool belt now. This is a triple bond. It's an alkyne. How on earth can we go from a triple bond like this to a C double bond O? Well, I hope that you tell me that we probably need to add something like water and acid, because that is one way that we can get an OH group onto the molecule. Okay, well, you're getting closer. So if we do this, CH3, CH2, carbon, triple bond, carbon, CH2, CH3. If we add water and acid, folks, this triple bond is going to go to a double, and 2 sites of attachment open up, one to the left and one to the right. You're going to look at these 2 carbons and you're going to say, where does hydrogen play? Markovnikov rule happens. Does it go left or does it go right? And you're going to tell me, it goes either way. It goes either way. Because the carbon to the left and the carbon to the right, they're both the same. Neither one of them have hydrogen on it. And I'll go, okay, that's fine. Let's just add it to the right-hand side here. Not a big deal. then that means the OH group has to go left. All right. Like we've done all the other times before, I'll just erase that hydrogen because we know it's supposed to be there. This forms an enol group. Look at that. We're using everything that we've learned in this lecture so far. This enol group is going to rearrange. That will rearrange, and that will go from a double bond to a single. That also erases the hydrogen up here. It does a switcheroo, and we create a new double bond between the C double bond O. That's the only way that we know how to make a carbonyl at this point. Now take a look at what you just did and compare it to what's up there. Third carbon in, I have my double bond O. Third carbon in, I have my double bond O. A total of 6 carbons all the way across, and a total of 6 carbons all the way across. Now, let's take a step back. Let's analyze this in a little bit more detail. What if someone wanted to be real smarty pants and say, let's not use water and acid. Let's use a mercury round. It'll give you the same product. That's also correct. Or what if someone wanted to say, let's not do water acid. Let's do the borane mix with the THF and then the OH and the H2O2 and the water. Well, it doesn't really matter here. It doesn't have a preference. Neither one of those have hydrogens anyway. We've seen that before in an example problem. They ended up with the same products. And folks, you would be correct here as well. That's also a correct choice. It's not a problem. Let's look at the products. We chose to put the OH group on the left-hand side. Well, what if that OH group went to the right-hand side instead? Would that be the same? I put the hydrogen to the left and the OH to the right. Well, take a look at it. Here, that double bond would have been there. The double bond would have been erased. This H would have been erased, and we would have formed a C double bond O at that carbon. And you're going to look at this and go, well, wait, this is 4 carbons in, and this is 3 carbons in. That's not the same. Yes, it is. Because you number closest to the N with the functional group. And that would be on the right-hand side. 1, 2, 3 in, I have a carbonyl. 1, 2, 3 in, I have a carbonyl. That would have also been correct. This gives you a little bit of freedom. You just have to be able to put it together in a way that makes sense for you. And sometimes these reactions will give you so many choices that they would be correct. Other times, the reactions will be so specific that there will only be one way at that point for you to make those products. Guys, this is also something that you can't Google. I'm going to repeat that. You can't Google this. So if you are working on a homework assignment or if you're working on a test, this is very difficult to go in and actually search for something like this. You really have to prove your chops in organic chemistry in order to answer these questions. How are you going to do that? It's not like naming. You know, if I gave you a name on a test or if I gave you a name on a homework, it's pretty simple to type that name in and let Google pop you out a picture of what the structure looks like. And you just copy it down and you don't think about it and you turn in your paper and you get a check mark and yay, everybody's happy. You can't do it here. Don't let these points eat away at your average because it will happen every single time unless you fully put the pieces together of the multi-step synthesis. So this is our first example of multi-step synthesis. And there's going to be many more. So I'm going to end this video with this question. How can we take ethine, react it, and get 2-bromopentane? That's up to you to figure out. So at the end of this video, jot this down in your notebook. See if you can come up with a way to go from the reagent to the product here. And look at the differences. You know you're going to have to elongate a chain. You also know that you're going to have to add a bromine on it. And that's where I would start. That looks like the major differences to me, doesn't it to you? Elongate the chain, get rid of the triple bond, and add a bromine. How are you going to do that? Put the pieces together. Everything is dumped on your bed, in the floor, in your bedroom. It is up to you to go through and start to organize it. And that's what these multi-step synthesis problems are. Take some time. No one says it's got to be done in 5 minutes. Take some time and think about it. Write down your answer. See if you can find something that works. And then come back and push play on the next video. And we'll see if you're going to be correct.